In this video, we will cover the chain rule for multivariable functions. But before we go there, let us just recall what the chain rule was in single variable calculus. So let's say that we have a function defined as f of x, where x is equal to some other function g defined in terms of t. Okay, then dy dt was being calculated as dy dx times dx dt. Right? We know this. We know this rule. We have used it so much in Cal 1 and Cal 2. So for example, if y is equal to sine of t squared, right? Here f of x would be sine of x, and g of t would be t squared. Then dy dt is equal to dy dx times dx dt. Okay, and derivative of y with respect to x is just cosine of x times derivative of x with respect to t is 2t. Now x is t squared, so you get 2t, right? 2t times cosine of t squared. Of course, this might look a little bit weird to you because you're used to solve this so fast, right? Without thinking what function is what and without even thinking about this rule. But this was just an introduction, just a reminder of what was the chain rule in a single variable calculus. Okay, so now let us write down what is the chain rule for a function defined in two variables. So if z is equal to f of xy is a differentiable function, of two variables x and y, where x is a function defined in terms of t and y is defined another function in terms of t, and these are both differentiable. Differentiable functions of t, then z is differentiable function in terms of z, and the chain rule follows the following formula: dz dt is equal to partial z partial x times dx dt plus partial z partial y times dy dt. And here maybe right away you can notice that for some, here I use this curly d, right? And here I use d with which we denote, right, just a normal derivative. So why that happens? Well, simply because z is a function defined in two variables. Z depends in x and y, so that's why when we are finding derivative of z with respect to x, we're using a partial derivative, because z is defined in terms of x and y. But then look at this, x is a function of t, so x just belongs to t, and y also just belongs to t, right? So, and you'll see we will use this diagram, we'll use this tree quite often in this section. So in order to find dz dt, First you have to go from z to x by partial derivatives, so partial z partial x, and then x just depends on t, so dx dt, plus derivative of z with respect to y. We're gonna get there using partial z partial y, and then y just depends on t, so dy dt. Okay, so let's do an example. Find dz dt, where z is equal to the product between x and y, and x is equal to cosine of t, and y is equal to sine of t. Okay, so by this formula right here, dz dt is partial z partial x dx dt plus partial z partial y times dy dt. Okay, so I'll write that formula here so that we can follow it. Dz dt is equal to partial z partial x times dx dt plus partial z partial y dy dt. Okay, so going back to the section, to the previous section, what is partial z partial x? This is the product x times y, so I treat y as a constant. Derivative of x is 1 times the constant y, that's only y, right, times dx dt is the derivative of x with respect to t, that's negative sine of t, plus partial z partial y. I'm differentiating z with respect to y, so I treat x as a constant. Constant times y prime with respect to y is the constant times the derivative of y, which is 1, so only x, times dy dt, y sine of t, so the derivative is cosine of t, right? And now express y and x using this definition right here. So this is negative from here, y is sine of t, so sine of t times sine of t, plus x is cosine of t times cosine of t, or simply this is cosine squared of t minus sine squared of t. And maybe some of you already noticed this identity. This is cosine of 2t. Okay. So let's do another example. Example 2. Z is equal to square root of 1 plus xy. Okay, x is equal to tangent of t, and y is equal to arctangent of t. Okay, so dz dt is equal to partial z partial x times dx dt plus partial z partial y dy dt. Okay, partial z partial x. Okay, so first I have derivative of square root of u is 1 over 2 times square root of u by the chain rule times u prime. Okay, I differentiate here with respect to x, so I treat everything else as a constant. Derivative of 1 is 0. Derivative of x times y with respect to x is just y, times dx dt is the derivative of tangent t, and that's secant squared t, plus derivative partial z partial y. By some symmetry, I'll let you guys figure this one out by yourself. It's very simple. Times, so that's partial z partial y times dy dt. The derivative of arctangent of t is 1 over 1 plus t squared. Okay, so let's simplify this if possible. So y is tangent of t. So here I have tangent of t, it's y. Oh, sorry, arctangent of t, my bad, sorry, arctangent of t for y times secant squared of t over 2 times square root of 1 plus x times y, and that's tangent of t times arctangent of t plus x, which is tangent of t over 2 times square root of 1 plus tangent of t, and here within the root times arctangent of t 1 plus t squared. Now what can we factor out? We can factor it 1 over square root of 1 plus tangent t times arctangent of t, and in the parentheses I'm left, well, 1 over 2 as a matter of fact. In the parentheses I have arctangent of t arctangent of t times secant squared of t plus tangent of t over 1 plus t squared. Okay, now let us do something slightly more interesting, and that's the case where x and y in the previous case are also defined in two variables. Okay, so if z is equal to f of xy is a differentiable function, defined in terms of x and y, where x is a function g defined in s and t, and y is a function h defined in terms of s and t, and these are both differentiable, in terms of s and t, then partial z partial s is equal to partial z partial x times, now we won't have dx dt or dx ds, we'll have partial x partial s because x is defined in two variables, plus partial z partial y plus, times partial y partial s. Similarly, partial z partial t is equal to partial z partial x times partial x partial t plus partial z partial y times partial y partial t. So looking back at that tree that we sketched for the first case, here we have z depending on two variables x and y, and each of these two variables depend on s and t. Then how are we going to get to partial z partial s? First we have to get to x, so z depends on two variables, so we'll get there by partial z partial x, and x depends in two variables, so times partial x partial s plus partial z, partial y, and y depends on two variables times partial y, partial s. Similarly, if we want to find partial z, partial t, first we get to x, looking for the partial derivative partial z, partial x, and then x dependent two variables, so partial x, partial t, plus partial z, partial y, times partial y, partial t. Okay, so let's do an example. Evaluate partial z, partial v where z is equal to 4e to power x ln of y, x is equal to ln of u times cosine of v, and y is equal to u times sine of v. Okay, so now we want to find partial z, partial v. So z depends on x and y, and x depends on u and v, so u and v, and also y depends on u and v. So because I just want to find partial z, partial v, I look at my root how to get to partial z, partial v. That's partial z, partial x times partial x, partial v, plus partial z, partial y, times partial y, partial v. Okay, so we can write that down. Partial z, partial v is equal to partial z, partial x times partial x, partial v, plus partial z, partial y times partial y, partial v. Okay, and now that's equal to what? Partial z, partial x, I evaluate this derivative only with respect to x, so 4 ln of y are treated as constants, so derivative of e to power x is e to power x, 4 e to power x times ln of y times partial x, partial v. Now I look at my x function, right? How much is partial x, partial v? You can actually evaluate that here on the side. Partial x, partial v is the derivative, partial derivative with respect to v of ln of u times cosine of v, which is equal to, you treat u as a constant, so that's going to be 1 over u times cosine of v, right? Times derivative of u times cosine of v. We said I treat u as a constant because I'm looking for the partial with respect to v, so the derivative of cosine of v is negative sine of v times u that's being treated as a constant. So partial x, partial v is negative u sine of v over u cosine of v, plus, now partial z, partial y, I look at the z function, everything that doesn't depend on y is being treated as a constant, that means 4e to power x, derivative of ln of y is just 1 over y. And now partial y, partial v, partial y, partial v is the derivative of u times sine of v with respect to v. I treat u as a constant, so that's u times cosine of v times u times cosine of v. Okay, so let's clean this expression a little bit. What is the common factor? 4 times e to power x, right? Here I can cancel these guys out. and sine of v over cosine of v, I'll write it as tangent of v. So I get negative tangent of v times ln of y plus u times cosine of v over y. And here you have to make a decision whether you continue simplifying this or not. In what sense? Whether you can whether you plug the value of x in terms of u and v. So we can do that. It's gonna simplify nicely for e to power, how much is x? ln of u times cosine of v. Okay, e to power ln of a is just a, so this reduces to 4 times u cosine of v. And here I have negative tangent of v times ln of u sine of v plus u cosine of v over y is u sine of v. And the only thing that we can cancel is here u, so the final answer is right, e to power ln of u cosine of v is just u cosine of v. Here I cannot cancel, I cannot simplify anything. Here I cannot simplify anything. And finally I cancel u and u, and cosine of v over sine of v is cotangent of v. And this is the solution. So that's how we find partial derivatives. Okay? Now we can do